Hello, everyone. We are Mary Saylor, George Brokos, Chris Wu, and Kat Schilling. Within our fire engineering biosensor stream, we created a website that introduces and evaluates specific COVID-19 diagnostics, where we will be presenting our research at the Fire Summit on November 16, 2020. Everyone should at least be familiar with the name COVID-19 or the coronavirus, as it has impacted all of us in many different ways. Below, I presented an image that shows you the structure of the SARS-CoV-2 virus, which will be discussed in more depth within our background information on the website. We are all aware about the vigorous spread of this virus that ultimately caused our world to fall into a global pandemic. As a result of this, there has been a high demand for rapid point-of-care diagnostics to determine who is infected in order for them to quarantine as soon as possible and hopefully limit the viral spread of this disease. Below shows the nose swab test, which is a sample that is used in a PCR-based method, which we expand upon within our website, in addition to various other emerging diagnostic methods. I'm sure most of you have experienced a time delay when receiving your results from a COVID test. This is one of the many reasons why scientists have been attempting to create alternative tests to avoid these setbacks. As you can see in the timeline below, the virus took only about 4 months from the first case to reach about over 1 million confirmed cases worldwide. Maybe if we had more rapid and efficient diagnostic tests, this pandemic would never have spread this quickly. Ultimately, diagnostic testing is the initial step towards breaking through this global pandemic and finally returning back to normal.
Our topic of COVID-19 diagnostics is closely related to our fire stream, which is engineering biosensors. Over the past couple semesters, we've focused on biosensor and aptamer technology. This is closely related to our project because COVID-19 diagnostics uses biosensor technology in order to detect the virus. Biosensors are devices used to measure or detect biological or chemical reactions. Our past knowledge that we have learned about biosensors during fire has been incredibly useful during our research of COVID-19 diagnostic tests. Our website is broken down into 4 subtopics. The first topic is the background on SARS-CoV-2 virus itself. We discuss the structure, timeline, and disease of the virus. The second topic is the current gold standard diagnostic method, which is reverse transcription polymerase chain reaction, or RT-PCR. This is the most used and accurate test that is available to the public. Our third subtopic is emerging diagnostic methods. Some methods we address are rapid antigen, nucleic acid amplification, and antibody-based tests. These are promising alternatives that will hopefully lead to more rapid and accurate results. Our last subtopic is evaluating COVID-19 diagnostic methods. Using assured criteria from the World Health Organization, we compare various diagnostic tests in order to better understand which is the most accessible, accurate, and rapid.
On our website, we compared the gold standard in lab diagnostic methods and a newer isothermal diagnostic method. You might have heard of PCR before. We used a variant of PCR known as RT-PCR, which stands for reverse transcriptase polymerase chain reaction. It is known as the golden standard lab diagnostic method. It is a nucleic acid amplification method that amplifies either DNA or RNA. It has both high levels of specificity and sensitivity. This method amplifies the viral genomic material present in a sample. First, you must take a sample from a patient, either DNA or RNA. In the case of COVID-19, it will be an RNA sample from a nasopharyngeal swab. Before we amplify the sample, we must lyse the sample with a lysis buffer and purify it with spin columns, a wash buffer, and an elution buffers. The viral RNA is combined with a master mix that contains primers that target specific regions of the viral genome along with the necessary enzymes and other components. Our RNA sample is now ready to be placed in a thermocycler for amplification. In real time, the fluorescent probes are used to track the increasing concentration of DNA. As you can see in the graph, the fluorescent signal increases as there are more copies of DNA made. More in-depth information on PCR can be found on our website under RT-PCR in the Methods tab. Now we will talk about an example of the newer isothermal methods, RT-LAMP, which stands for reverse transcriptase loop-mediated isothermal amplification. The major points of LAMP is that it is isothermal, It amplifies rapidly. It uses 4 to 6 primers that recognizes 6 to 8 regions of the target nucleic acid. It is both cost efficient and it is time efficient. More in-depth information on LAMP can be found on our website under RT-LAMP in the Methods tab. A simple comparison of RT-PCR versus RT-LAMP shows that RT-PCR is not isothermal. The temperature cycles up and down, while RT-LAMP is isothermal. RT-PCR needs 2 primers, the forward and reverse primers, whereas RT-LAMP requires 4 to 6 primers, as you can see. RT-PCR takes longer to accomplish, 45 minutes to an hour, whereas RT-LAMP is faster. It can take anywhere from 15 to 60 minutes, however, it'll typically take less than 30 minutes. RT-PCR has lower product yield, whereas RT-LAMP has a higher product yield. Visual detection is not possible for RT-PCR, whereas it is possible for RT-LAMP. Lastly, PCR is easier to multiplex, whereas RT-LAMP is more difficult to multiplex.
Our research into COVID-19 was very interesting. Here we show a table that compares molecular tests such as RT-PCR and RT-LAMP, antigen tests, and antibodies. This table compares these 3 different methods based on accuracy, how long it takes to get the information, limitations, and results. The next part of the research focuses on what went wrong in regards to testing. For example, issues with primer development and limited testing supplies led to a slower diagnostic response. And the fact that the FDA only certified a select number of labs, which they then eventually allowed other research labs or companies to run these tests, which harmed our ability to react and deal with the virus accordingly, initially. In the last part of the research, we describe taking what we learned from COVID-19 diagnostics and using it for other pathogens or viruses, and for finding a more efficient and accurate model for testing for COVID-19 itself. All of our research came from a wide range of sources, from journals, websites, videos, and many more. It can all be found here on the resource page of our website. Next, we have the frequently asked questions, which we have some questions that came from friends and family, but please, feel free to ask any more you have while going through the website. If you want to see the people behind the website, see the About Us page. Finally, here are the resources that we use for videos specifically. Thank you, and have a nice day.